In this lecture, I will explain efficiency and peak inverse voltage. Efficiency is defined as ratio of DC power available at the load to the input AC power. Efficiency is denoted by eta. Eta percentage is equal to P load, the power available at the load, divided by P in, the input AC power, multiplied by 100. And we already know power is equal to VI. V is equal to IR, so power is equal to I square R. We can write P load as I DC square multiplied by R, where R is the load resistance, divided by P in is equal to I RMS square multiplied by R, where R is the load resistance. This R and this R will cancel out, and I DC is equal to Im, the peak value of current, divided by pi, and I RMS is equal to Im divided by 2. So we have Im square divided by pi square divided by Im square divided by 4. We can cancel out the two Im squares, and we are left with 4 divided by pi square. When you solve this, you will have efficiency. When you solve this, you will have efficiency equal to 40.56%, which is very low. 40.56% efficiency is really low efficiency, and this is one of the disadvantages of half wave rectifier. When we study full wave rectifiers, we will see the efficiency is much larger than 40.56%. This is all you need to know about the efficiency of half wave rectifier. Now we will move to the peak inverse voltage. Peak inverse voltage is also called as peak reverse voltage, PRV, where P stands for peak, R stands for reverse, and V stands for voltage. So what is peak inverse voltage? The maximum reverse bias voltage that we can apply across the diode before entering to the Zener or breakdown region is called as peak inverse voltage. This is the maximum reverse bias voltage that can be applied across the diode before entering to the Zener or breakdown region. I will quickly draw the circuit of half wave rectifier so that we can calculate the peak inverse voltage of the diode used. This is the diode that we are using, and we have to calculate the peak inverse voltage of this diode. I will connect the source. The maximum voltage or the peak voltage of the source is equal to Vm, and load resistance is equal to R. This is diode D, and I will calculate the peak inverse voltage, and to obtain the PIV, the diode must be reverse biased. So this will be the polarity of input voltage, minus plus. P side is connected to negative terminal and N side is connected to the positive terminal. I will replace this diode with its equivalent model, and the equivalent model is open circuit. There will be no current in this circuit. Current I is equal to 0 because the circuit is open, and the output voltage across this resistance is equal to 0 because current is equal to 0. And let's say peak inverse voltage is equal to V. I will calculate the peak inverse voltage by using the KVL, Kirchhoff's voltage law. We have minus of Vm plus V equal to 0, so V is equal to Vm, and V is nothing but PIV, so peak inverse voltage is equal to Vm, the peak value of source voltage. There is one condition that we have to follow. Peak inverse voltage must be greater than or equal to Vm, because if peak inverse voltage is less than Vm, diode will damage. Peak inverse voltage is the maximum reverse bias voltage that we can apply across the diode, and in this case we are applying Vm across the diode, and Vm is greater than peak inverse voltage, so diode will damage. And to protect the diode from being damaged or to retain its properties, we have to make PIV greater than or equal to Vm. This is very important condition that we must follow. So this is all you should know about the peak inverse voltage. Peak inverse voltage is equal to Vm, the peak value of the source voltage. From the next lecture, we will start full wave rectifiers. If you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.